Chapter 6, we're going to be taking a look at rational numbers. So if you have had number theory, this is where we sort of left off from number theory. If you haven't, it's not a problem. But the first 5 chapters of this book really focus on the elementary grades through whole numbers and integers and things like that. And so we work up to about 4th to 5th grade, somewhere in there. And this picks up kind of where that leaves off with rational numbers. Rational numbers is another phrase that you might remember as being decimals, fractions, things like that. So that's what we're looking at in this chapter. So fraction is our first definition that we're going to look at here. This is any number of the form a over b, where the b is not 0. So this can include anything: positives, negatives, square roots, pi. You can put them on top, you can put them on bottom. Anything in this form is what we would consider a fraction. But not all of those things that I just said are considered rational numbers, but they are fractions. The number that's on top is called the numerator, and then the value that's on bottom is called the denominator. Now, if we take this idea of fraction and we narrow down the things that we allow a little bit, we get rational numbers. In particular, we have to be able to write this where the number on top and the number on bottom are integers. And if we can do that, then we call it a fraction, a rational number. For example, if you had the number 2.5 over 7, that's not an integer over an integer, but it could be changed to become 1. I could actually multiply this. We'll talk more about how we do it, but we could multiply this by 10 on top and bottom. Now I have 25 over 70. That is an integer over an integer, and so it's a fraction that is a rational number. But not everything has the ability to be manipulated to be integer over integer, so there are things that you've seen maybe in a trig class or a geometry class like pi over 3. This is not an integer. I can't do anything with pi to turn it into a decimal that ends, to then turn it into an integer. Like, I can't do it. So this doesn't work. Or if you ended up with something like square root 2 over 2, maybe you saw that in some algebra course somewhere as an answer to something. It's not a rational number because by definition, square root of 2 isn't rational. It doesn't have a closed way of writing it at the end. So this isn't a rational number. It's fraction. Both those are fractions, but they're not rational. There are 4 basic uses of rational numbers. Hang on. Well, that's okay. I'll leave those on here. Solutions. So they can solve equations. So solving equations like 2x equals 1. So if I have 2x is equal to 1 and I solve it using algebra stuff, from high school, you'd get x is 1/2. Well, in order for that to work, 1/2 has to be a number. That's a rational number. Partitions. So a partition takes something and it separates it into parts. So something like 1/4 of my paycheck goes towards gas. 1/3 of my paycheck goes towards tuition or something like that. That's a partition. Ratio. You've all heard of teacher-student ratios, right? That's an example of one. So a ratio talks about a comparison where you're comparing two things, teachers and students in this scenario. So if a teacher-student ratio is 1 to 12, for example, you might write it as 1 over 12. That is a way to write a ratio. Probability. So probability is the likelihood of something to happen as a general statement. So an example of probability might be something like this. For a standard 6-sided die, the probability of rolling a 4 is 1 out of 6 because there's 1 4 and there's 6 total sides. So these are 4 basic uses, places where we see rational numbers used. We'll explore some of these more in depth. Probability, we're going to do a whole chapter on it. It's chapter 9. Ratios is going to come into play in this chapter, in chapter 6. Partitions will kind of be sprinkled throughout. We actually won't see solutions used in a sort of concrete sense, but again, sprinkled throughout as well, where it's a solution to something else. Okay, so what we're going to do is we're going to take different images and we're going to figure out how much of the image is shaded in. And some of these have sort of some red flaggy kind of things where students make mistakes. They think about it incorrectly. And we want to draw our attention to those as well. So can you tell on fraction, or on the box A, the picture A, what fraction of this is shaded in?
1/6.
It is 1/6. Now, if you're thinking, isn't it 1/4, you're not alone. It looks like there's one box shaded in and there's 4 boxes. The problem is the boxes are not equal in size, right? Right? This is like looking at the piece of pizza. I have an image later here, letter C looks like a pizza kind of, right? And taking the biggest piece and saying, but I only ate 1/6. And you're like, but it was a big 1/6. Well, then it's not really 1/6, right? This is 1/6. If we were to drop in these lines right here, they're not very straight, but if we were to drop them in and create 6 boxes, rather, that are all equal in size, you can see that only one of 6 equal sized pieces is shaded in, right? How about B? How much is shaded in? It should be 1/4. Kind of looks like it's 1/5. There's 5 boxes. But again, they're not equal in size, right? So if you want to think about this, what we can actually do is we can sort of remove the way that this is shaded. And we can drop in this piece to make, again, equal boxes. That's not the only way to change that diagram and to find this out, but it's a decent way of doing it. But can you see how on both A and B, there's sort of a picture that leads you incorrectly to a certain answer based on the size of things being equal or not equal? What about on C? What fraction is here? Those are all equal in size, or at least they're attempting to be. It is 2/7. Okay, so if you really count all of them, there's really no confusion here. The problem is that this is an image that looks very familiar to us. It looks like a pizza, doesn't it? How are pizzas normally cut, though? Usually into 8ths. So if you're not really counting and you're just looking at a familiar to you image, it'd be really easy to say that this is 2 out of 8, wouldn't it? It would. Okay, so again, there's nothing that's like wrong about the picture, but we're sort of led to do something incorrectly. Last question, and we'll be stopping for today. This is a very distinctly different picture than the rest of them. All the other pictures are one solid image. They're a whole that has been partitioned. That's not what's going on here. This is a collection of objects, right? This is more like a ratio. How many are shaded? How many are not? From a whole picture perspective. So, how many are shaded versus how many are not? What's the fraction that you see here? 7 out of 12. Again, there's nothing about this one, even that's sort of misnamed or anything like that. But the image is quite different because of how it's being portrayed. These are individual objects, not objects that are all one object split into pieces. All right, we will stop there for today.